So have you ever actually stopped to think about how a simple glass of water sitting on your desk shares the exact same fundamental building blocks as the cutting-edge AI systems designing life-saving medicines right now? I mean, it sounds like pure science fiction, but honestly, it's just chemistry. Welcome to this explainer. Today, we're diving deep into the invisible architecture of matter. We're going to trace this wild journey from the basic structure of a single atom all the way up to how modern machine learning is completely revolutionizing our physical world. Let's get right into it.
Okay, picture this. You've got a solid block of material and a perfectly sharp knife. What happens if you slice it in half, and then you slice that half in half, and you just keep going forever? Like, can you actually do that? Well, the ancient Greek philosopher Democritus asked himself this exact same thing, and he realized, eventually, you're going to hit a wall. You'd reach a piece of matter so incredibly tiny, it literally couldn't be divided anymore. He called this the atomos, which in Greek translates exactly to indivisible.
But here's the thing. For a really long time, atoms were just that, a philosophical idea. It actually took centuries to pin them down in reality. Fast forward to 1827, and this botanist named Robert Brown is looking at pollen grains in water, and he notices them mysteriously jiggling around, pushed by some invisible force. Fast forward again to 1905, and a young Albert Einstein comes along and mathematically proves that this jiggling, what we now call Brownian motion, was actually caused by invisible atoms physically crashing into the pollen. Einstein finally settled the debate. Atoms aren't just ideas, they are real, physical things.
So, let's zoom in a bit. What does one of these things actually look like? Think of an atom kind of like a squishy ball of clay. Right at the dead center is the nucleus. It's this heavy, dense, and frankly, kind of boring core made up of positively charged protons and neutral neutrons. They really just sit there, held tightly together. But swarming around that core, that is where the magic happens. You've got these ultralight, negatively charged electrons doing literally all the interesting chemical work, jumping around and forming the connections that build our entire universe.
Now, if you want to know the true soul of an atom, look at its protons. If you have exactly 47 protons, you always have silver. No exceptions. But what about those neutrons we mentioned? Well, neutrons act as a critical buffer, basically keeping those positively charged protons from repelling each other and just ripping the whole nucleus apart. And here is where it gets super interesting. You can actually change the number of neutrons without changing the element itself. Silver, for example, usually has 60 or 62 neutrons. We call these variations isotopes. So they have different masses, sure, but their chemical identity remains exactly the same.
And speaking of chemical identities, I want you to think about the number 118. That is the total number of known elements in the entire universe. It's crazy to think about, right? Think of them like a strictly defined set of Lego bricks, or 108 unique colors of molding clay. You don't change the individual bricks, you just rearrange them. Literally everything, from the screen you're looking at right now, to the air you're breathing, to the living cells in your own body, is just a different combination of these 118 basic building blocks.
So, to keep track of all these building blocks, we rely on the universe's ultimate cheat sheet, the periodic table. It's actually brilliantly simple once you look at it. Elements in the same vertical group, the columns, share the exact same number of outer shell or valence electrons. That means they have strikingly similar chemical personalities and behaviors. Meanwhile, as you move across a horizontal row, or period, you're really just increasing the atomic number. You're adding protons and electron shells, which just makes the atoms heavier and larger.
Which naturally leads us to a massive, fundamental question. If these atoms are perfectly fine existing on their own, why do they bother combining to make stuff like water or plastic or DNA? Well, it all boils down to one word: energy. Every single atom in the universe is desperately trying to reach a state of lower potential energy. The ultimate dream for an atom is to have a completely full outer shell of electrons. They all basically want to be like those noble gases on the far right of the periodic table, totally aloof, completely stable, and not needing anyone else to feel complete.
So how do they get there? Let's quickly walk through the hierarchy of forces holding our universe together. We're looking at everything from the most powerful chemical bonds, like ionic, covalent, and metallic, all the way down to the weakest fleeting attractions, like hydrogen bonds and van der Waals forces. Let's break the major ones down. First up, we have ionic bonds. Honestly, just think of this as desperate theft. Going back to our clay analogy, some atoms, like fluorine or chlorine, are incredibly electronegative. They have this massive, almost overwhelming pull for electrons. So if an atom like chlorine gets near a willing donor like sodium, which, by the way, wants to get rid of an extra electron anyway, chlorine will aggressively tear that piece of clay right away. One becomes negative, the other becomes positive, And that resulting magnetic attraction locks them together into a rigid crystal structure. That's exactly how we get table salt. But, not all atoms want to steal. Let's move over to covalent bonds and see how this builds a completely different type of structure. Here, instead of aggressive theft, we have equal, or at least mostly equal, sharing. Two atoms basically mash their clay bodies together so their electron clouds overlap. By sharing those valence electrons, they both get to pretend they have perfectly full outer shells. This is exactly how hydrogen and oxygen come together to happily form the familiar molecules of water we drink every single day. And then we have metallic bonds, which are just wild. Metals don't share electrons just between two neighboring atoms. Instead, they release their outer electrons into this giant delocalized sea. It is a completely promiscuous playground where electrons just flow freely between all the positively charged nuclei. And this brilliant little structural quirk, it perfectly explains why metals can conduct heat and electricity so beautifully, and why you can bend and hammer a piece of solid copper without it shattering into a million pieces. Now here is where we pivot from the macroscopic world we can actually see right into the pure, unadulterated weirdness of the micro world. When we talk about heavy, predictable things, like cars driving or a baseball flying through the air, we use classical mechanics. It's continuous and it intuitively makes sense to us. But when we look at electrons and atoms, they are so ultra-light that the rules change entirely. We cross over into the realm of quantum mechanics, where energy is discrete and behavior isn't certain at all. It's purely probabilistic.
So the absolutely crucial point here is that electrons don't actually orbit the nucleus in perfect little circles like planets around a sun. That is a total myth. Instead, thanks to Schrödinger's equation, we know they exist in probability clouds called orbitals, specifically s, p, d, and f orbitals. Try to imagine them as fuzzy, vibrating three-dimensional spheres or dumbbells of clay. The denser the cloud is in a specific spot, the more likely you are to find an electron hovering exactly right there.
Okay, so we know the rules. We know about atomic nuclei, we know about those eager valence electrons, and we've got a handle on quantum probability clouds. But why does this actually matter to you? How does knowing this microscopic architecture change our macroscopic future? Well, it's a massive paradigm shift. It takes us from being a species that merely discovers what nature has already made to a species that can deliberately manipulate and build the world exactly as we want it. And this is exactly where the magic of modern computing enters the frame. We are finally moving past the era of trial and error chemistry. Because we deeply understand these physical and quantum rules, we're now using artificial intelligence to do some absolutely incredible things. I mean, systems like AlphaFold have successfully predicted the 3D structure of 200 million proteins. That's essentially every single protein known to exist. Beyond biology, we're using AI networks to optimize complex chemical synthesis, design entirely new biodegradable plastics, and discover incredibly efficient materials for next-generation solar cells, and we're doing it all block by block, atom by atom.
In fact, a fascinating 2025 research paper published in the International Advanced Journal of Engineering, Science, and Management highlights this exact revolution. It points out how machine learning models are now completely bypassing traditional, intensely slow quantum mechanical computing. Instead of forcing computers to manually calculate the agonizingly complex physics of every single electron, neural networks have simply learned the underlying patterns. They can now predict molecular properties, toxicity levels, and binding affinities almost instantly. It is utterly transforming the speed and scale of chemical science.
Which really brings us to our final thought. As a material science professor at MIT recently pointed out in a lecture, we live in the age of atomic design. We have finally realized the ultimate dream of understanding the atoms so deeply that we can literally put them anywhere we want. Our mastery of these microscopic rules means the biggest question facing science right now is no longer can we make it. The real question we have to ask ourselves now is, what should we make? Thanks so much for joining me on this explainer. I'll catch you next time.